Welcome. In this video we'll talk about implicit differentiation. So what is implicit differentiation? Implicit differentiation is some kind of differentiation or a situation of differentiation in which the function is not explicitly, it's not clearly presented to us. Thus far we know how to find derivative of functions, but in all these functions we find, we just say y is equal to something like 3x squared plus, let us say, 10x, or we say f of x is equal to e raised to 2x plus 3. So in all this function, what we do is that this function is clear that we want to differentiate some function f of x or some function y. It's clear, it's explicitly presented or shown to us by the expression itself what we want to find the derivative of. But some situations come into picture when we cannot have this facility of this function be explicitly shown to us. Look at these examples here. 6x cubed plus 3y cubed is equal to e raised to 2x plus sine of y. We cannot solve this thing using these rules. Why? Because we have y cubed and here we don't have y cubed. All these powers here were 1, 1, 1, but in this case it's y cubed, which means if you want to take this y to put it explicitly as we usually do, we would have to put all this to the other side and then we'll end up having only y. But this can be a very difficult task because it may give us a very strange or very difficult expression that will consume time to solve. What I mean is that our function is 6x cubed plus 3y cubed is equal to e raised to 2x plus sine of y. So if you want to make this explicit, what we do is we push this to the other side, we push it here, and then this 3 that was multiplying will turn out dividing there. So we end up having y cubed is equal to e raised to 2x plus sine of y minus 6x cubed, all this divided by 3, and our y, which now is explicit, is equal to the cubic root of e raised to 2x plus sine of y minus 6x cubed, all this divided by 3. Now this y is explicit, but it's very difficult to solve this derivative, to find the derivative of this function. It's very difficult. We have to use some rules of the roots that we have, and then we have to pull it out, and then we are going to have a case in which we have to use the chain rule, and this is just time consuming. So to avoid that, we use the implicit differentiation method. What basically says is that I differentiate the function, I see whether the function is with respect to x or y, I differentiate it, and I consider that all these functions are with respect to x. So how do we do this? Well, we differentiate the function and we show with respect to which variables we have differentiated the function. Look at this. What we'll have is that derivative of this, which is a function of x, and then I have to show that it is a function of x and with respect to x. This, which is y, and y is a function of x, I have also to show that it is a derivative of y with respect to x. And likewise I do for all of them. What I'm saying is this, derivative of this using the power rule. So 3 will come down and then we know the rest. So we have 18x squared dx by dx. We differentiated this function of x with respect to x, plus we come to this side now. 3 into 3 is 9 y squared dy by dx. We differentiated a function y, which is a function with respect to x, we differentiate with respect to x because we're considering that y is a function of x, is equal to derivative of this is 2 e raised to 2x dx by dx. This is a function of x alone, and plus cos of y dy by dx. So in all this, what we did is just differentiating the function of x and showing that is the derivative of x with respect to x. The functions of y were derivative of the function of y with respect to x, and likewise. So the constant term was this dx in all the terms. So afterwards, what do? We have dx here and have dx here, but dx by dx and dx by dx means we have a numerator equal to the denominator. So what we do is we simplify it. As we simplify it, we have 18x squared plus 9y squared dy by dx is equal to 2e raised to 2x plus cos y dy by dx. So now we have this term having dy by dx and this term also having dy by dx. So we can just take them and put in one side, and those who do not have dy by dx we put in the other side. We end up having 9y squared dy by dx minus cos y dy by dx is equal to 2e raised to 2x minus 18x squared. So this dx by dy by dx is common in both these sides. So what we do now is we just put dy by dx is common to 9y squared minus cos y, and this is equal to 2 raised to e raised to 2x minus 18x squared. So this is multiplying with dy by dx. So when it passes to the other member, it divides. So what you're going to have is dy by dx is equal to 2e raised to 2x minus 18x squared divided. This was multiplying. When it comes to the other side, it's dividing. So 9y squared minus cos of y, and now we have the derivative by the implicit differentiation method. So we have the rate of change of y with respect to x is equal to this. So dy by dx, which can also be represented, so dy by dx, which can also be represented as y dash, is equal to 2e raised to 2x minus 18x squared divided by 9y squared minus cos y. And it's done. For this example, what we do is the same. This is a function of y, this is of x, this is of y, this is y, and this is of x, and this is of y, and this is of x. So what we do in this case, we just find the derivative of this function of y with respect to x, and all this y, x, and y and x, they're all going to be with respect to x. So what will change is basically the numerator when we'll be representing the differentiation. So for the case of y, we'll have the derivative of this multiplied by dy by dx, and in this case, because the function of x, will have dx by dx, and again here dy by dx, and here dx by dx, and then we simplify dx by dx because it gives us 1, and then we put dy by dx isolated, and then we have the derivative of that function implicitly.